This is problem 1420. It's on page 600. A 50-gram bullet is fired with a horizontal velocity of 500 meters per second into a 4-kilogram wooden block, which is at rest on a frictionless horizontal surface. Determine A, the final velocity of the block, and B, the ratio of the final kinetic energy of the bullet and block to the initial kinetic energy of the bullet. Okay, now, one of the things they don't mention here, but I think is their intention, is that when the bullet's fired into the block, we're not really interested in what happens until the point in time where the bullet becomes embedded in the block. So they didn't say it, but I think what they're trying to get at is that the two become one system. They become coupled together. It's a perfectly plastic collision. Okay? So let's see if we can figure out things they've asked for. We want the final velocity of the block. I think what they mean is the velocity of the block plus the bullet together. Does that make sense? Okay. So since it's a frictionless surface, if we were to take the bullet and the block as a system, are there any external forces? No. Should we take the bullet by itself, or the block by itself, or the bullet and block together? What do you think? Together, right, because that eliminates all of the forces that we can't account for. Otherwise, we can't solve this problem, right? So this would be mass of bullet times velocity of bullet initial plus mass of, I'm not going to use block, let me use W for wood, times velocity of wood initial equals, again, all the forces are internal to the system, right? There's force from the block on the bullet and the bullet onto the block. They're internal. So we can just say mass of bullet, velocity of bullet final, plus mass of wood, velocity of wood final. Noting that the velocity of the bullet and the wood are the same, we can just write VF. Also noting that the wood is not moving initially, we can get rid of one of those terms. So this looks a lot like what we had I think in the last problem. The first question is to find the final velocity of the block. Well, that's pretty easy. The final velocity of the block and the bullet, we can just solve for it, is the mass of the bullet divided by the sum of the mass of the bullet and the wooden block multiplied by the velocity of the block, the bullet, excuse me, initially. Okay, so we know that the mass, let's see, 50 grams and 4 kilograms, 500 meters per second. So, let's see, 0. Can't think for some reason. 50 grams, so 1, 2, 3. So 0.5 kilogram bullet divided by 0.05 plus the mass of the wooden block is 4 kilograms. Keep forgetting my numbers. Yeah, 4 kilograms. And 500 meters per second. So we can calculate the final velocity pretty easily. In fact, when you do that, you come up with, or I came up with, 6.1728 meters per second, because the two are combined, right? And the momentum of the system is conserved. The initial momentum equals the final momentum. Okay, so that's part A. Part B asks about energy loss. And really what they're saying, they say the ratio of the final kinetic energy of the block and the bullet to the initial kinetic energy of the bullet. So let's take that as an actual ratio. So energy ratio. So they want the kinetic energy final over initial. So it's a percentage basically. Okay, so final energy is going to be 1/2 mass of wood plus mass of bullet times final velocity squared. Help me write the initial energy. What should I write for the initial energy? Just the bullet, right? The bullet's the only thing that has energy. It has kinetic energy, so 1/2 mass of bullet velocity of bullet initial squared. You see that the halves go away. We don't need those two. Okay, if we're just interested in the ratio of these energies. And let's keep playing with it just a little bit before we plug in numbers. Let's see if there are any more simplifications. We have an equation for the final velocity in terms of the initial velocity. So if we plug in mass of wood plus mass of bullet divided by mass of bullet, now I'm going to have the square of the square of the velocity ratio. So if I plug in for VF, if I plug all of this in for VF, and I'd have MB over MB plus MW squared, VBI squared. Okay, so that takes care of this term. Divided by, well, let's not do it that way. I've pulled this piece out over here. So divided by VBI squared. Notice that those two go away. And you'll notice also then that this energy ratio is just a mass ratio. So let's see, you have just MB over MB plus MW. So that's going to be whatever this number is, 0.05 over 4.05. Okay, and that comes out to 0.0123. Notice it's non-dimensional. What it means is that 1.23% of the energy is not, I don't want to say conserved, but stays in kinetic energy. There's not much. Okay? Does that make sense? Yeah, I see confused looks. Any questions? Yes?
Would it be a whole lot less algebra to figure out? Because it's easy, you know, 1/2 MV squared, just solve it for both, because it's two numbers divided by 2.
You could. Sure,
Instead of
yeah.
top of each other.
You should get the same thing. The only reason I did this is because I like to work in symbols as much as possible, and you should move toward that. I know most of you guys like to work with numbers. Put a number in for the variable, and that'll come back to bite you. So I did this just so that you could see. You find some interesting things. You find that actually the initial velocity of the bullet is not all that important. Right? It canceled out. Once you've got the masses, that's all you really need. We didn't even need to know how fast it was going. So I could give you a question now that says a bullet impacts a block. Here's their masses. What's the ratio of the energy? The initial and final. And if you didn't have the initial velocity, you might say, well, how on earth am I going to figure this out? Well, you can still figure it out, which is kind of interesting, I think. Questions, comments? Here's something kind of interesting, thinking from trying to use a bullet to take down an animal. Notice that the mass of the animal, the wood essentially, the bigger it is, the less energy is kept in the tube. Right? So using a small bullet is a good thing by comparison to the mass of the animal you're trying to take down. Because most of the bullet's energy, it'll be more efficient, right? Most of the bullet's energy, you want it to convert into some other form. You want it to do work cutting, right? You don't want the animal to suffer, so you want it to die as quickly as possible. So you want to inflict damage very quickly and accurately, right? So actually having a large animal with a small bullet looks like a good thing. It's not like it's going to knock it off its feet. Mythbusters did a whole movies myth a couple times, and they shot various dummies and things with bullets. Because in the movies, you know, the guy gets shot and he, you know, is thrown off his feet, off the ground. It doesn't work that way. This is what happens. What happens is the bullet goes in and converts its kinetic energy to cutting up things on the inside, and that's bad if you're the one on the receiving end, right? So anyway, it's just interesting that there's so much that's way off in movies. And if you start critiquing the physics in movies, you will very quickly not like the movies anymore. Questions, comments?